Swayam Prabha. Digital India. Educated India.
Okay. So what we looked at was different types, and I was talking to again Professor Aragappan over the break, and he said there's Wolfram Research Alpha online version where you can solve all these differential equations. You don't have to do the work; it does the work for you. So something to Wolfram Research Alpha. It's called, I think, Wolfram Alpha. Yeah. So there used to be a program called Mathematica. I don't know if you're familiar. So that's from Wolfram Research. So you don't need to have a copy on your system, but you can do this online. It's got quite a few basic free features. I didn't know about it actually. So anyway, our goal here is not to solve differential equations, but to study the characteristics of the solution. So let's call these case 1 and case 2. And now that you're familiar with, and we'll see case 3 also, but let's start with case 1 and study what happens. So case 1, you have the load is constant over time. This is TD. Important terms to remember: peak value versus time. So the expression is m x double dot plus sorry, not x dot, is equal to p naught. And so this can be broken down into mx double dot plus omega n square x equal to 0. This is the homogeneous part to get xh, and then the same thing is equal to p naught to get the particular solution. And the homogeneous solution, we have seen, this gives us the free vibration problem. So let's look at the particular solution problem. And in this case, a typical particular solution is, when you start with it, it is in the form of the function itself on the right hand side. So in this case, it is, let's say, some constant multiplied by p dot. So if you see first derivative, since it's constant, both of them are constants, x double dot p is equal to again 0. And so what you get here is m x double dot p, or plus you have here omega n square x p is equal to C1 p naught, or C1 we can just equal to C1 equal to 1, because let's just say p naught is the absolute value. So from here, if you look at it, applying these conditions and expanding it out, you get xp is equal to p naught by, I am not showing you the details because we will focus on p naught by omega m omega n x square. It is basically simply substituting. You are going to substitute here, so this goes away. So what you have is, there is m here also. So xp is equal to p naught by omega n x square. Solution is actually right there. So the total solution now is x is equal to xh plus xp. So this is a cosine omega n t plus p naught by m omega n squared. So, now let us say at t equal to 0, x is equal to 0. It starts with 0 initial position. So, now you have 0 equal to, this is a, plus p by m omega n square, or a is equal to negative p naught by m omega n square. So, this is one. Then, so if I substitute it back, I get x is equal to find a basically. So, now I have a. So, x is equal to minus p naught by m omega n square cosine omega n t. You might be wondering why I am writing each one of the steps, it will be evident soon. So, in a simpler form, I can say x is equal to p naught, and any questions so far? No magic out here, no hand magics, right? Any questions so far? What is the, let us look at, take a moment, step back, can stop writing and study this expression. What does the first term represent? It looks like a complex form, right? P naught m omega n square. What, yes, what deflection? Always step back, take a breath. Static deflection, right? So, the first term, very good. So, omega n square is square root of k by m. So, k is equal to m omega n square. So, the first term here is p over k, which is delta static. Okay. Now, question is, what is the maximum displacement and again remember reminding you this is constant blast load, and when does it occur? So, what would you do to get the maximum displacement? Slope has to be determined, that is one way. Any other easier way of doing it?
The term should be 1 minus cos omega t.
Should be 1.
Should be maximum.
Should be 1. Okay, so I have two answers. It is?
2, like cos or
minus 1, right? So, it can go to 2. So, the answer to that is the maximum displacement is when? What's that? Cosine? Yeah. So, x, we can now say x max, which is, let us say, delta dynamic, is delta static multiplied by, quite often we are not interested in the response history, right? All we are interested is in the peak response. So, we get a very sort of a baseline, it always grounds us. Delta dynamic is 2 times, and what are the assumptions on these conditions? So, when is these, remember the assumptions part that we should never forget. What were the assumptions on this? Constant P naught, constant P, what else? Undamped, what else? Initial is 0, one more. Elastic behavior. Remember we started a, see it's easy to lose track. So, elastic, more undamped, we are talking of undamped, the other one more was mentioned, but more importantly under these conditions delta dynamic is 2 times delta static. What does elastic mean? No damage at all, right? Elastic, rebound. Structures, do they behave that way? So, you might say why is it always maximum of 2, but what it does is it gives us an idea where you should be. If you are getting 20 times delta static for something, you know your answers are not quite right. So, that is the first lesson to be kept in mind, that the dynamic displacement is less than 2 times static displacement. Is approximately 2 times static displacement, and you can always calculate the static displacement. Then the next idea is when does it occur? In other words, at T max any ideas? What would you do, suppose I ask you the question to find out when it occurs, where would you start? Somebody else who is not answered, even if it is wrong. Right, we will give a chance to somebody else. He is itching to answer. Anybody else wants to take a shot? Going once, twice? There are not too many choices. Really think of, narrow down what choices do I have, and then there is one choice, that is it, which involves time. There is a variable, there is a quantity in there that involves time. You are looking for answers for time, right? And there is one variable that gives the time, and you have, yeah. Soundar Pandyan, you wanted to say something? No? So, what is the quantity that involves time here? It is right? Okay, let me make a little more clue. Okay, right there. Cosine omega n t, right? That is the only term in this whole expression that has time as a variable. So, you have, that is how you move forward. So, cosine omega n t is equal to, what we had here was 1, right, negative 1. That is, so at Tm, right, you are with me on this. Now, when is cosine omega n t equal to negative 1? N pi, right? Or here so omega n t m equal to, let us say, pi. Now, omega n is also in terms of the time period. What is omega n in terms of the time period? Remember, 2 pi by Tn. The reason why I reviewed all those. So, if I now put this here, 2 pi by Tn, Tm is equal to pi, get rid of these two. So, what do I get? When does it occur? Tn by 2. See, look how the dynamic characteristics, you can easily calculate Tn. Now, you know, so Tn, Tm is equal to, this is another significant results. So, we come to the second story number 2. This is, we all like stories, right? So, story number 1, this is the first story. Where was that? And here it occurs at Tm. So, max displacement is at. So, what is an important thing? Everything seems important. I seem to use that word. Here it depends on the structure characteristics. So, keep that in mind. Now, this tells us that the response depends on the load duration and it's got something to do with the duration of the load. We will do one more thing, and the natural time period. So, let us look at the, so this is the, let us say, story number 3. For this, let us go back to x is equal to delta static multiplied by 1 minus cosine omega n t. Omega n is 2 pi by Tn, right? Would you object? You'd be upset if I said, if I wrote it like this? No, thank you. If you were, I would have stopped this point right there. So, this is delta static multiplied by 1 minus cosine of omega n is 2 pi 2 pi by t, right. So, 2 pi Td by Tn, then Td by Tn, and not okay, omega n, let me do one thing. And there is also t, right. Yeah, Td, let me make sure, 2 pi by Td, Td over Tn, okay, this is fine. So, this is now delta static multiplied by 1 minus cosine of 2 pi. So, here I will put these expressions a little differently, Td by Tn multiplied by 2 pi by Tn, which is a constant, multiplied by time. So now you see the response depends on the ratio of the load duration to natural time period. So let's consider the case we just looked at. Case 1 is what we just looked at, Td by Tn equal to 1/2. The max response is at Tm is at Tn by 2. So in this case, the max response, what it means is, if I do this, what I am saying is max response occurs when at the end of the load duration. So now we are now expressing the max response because load duration is important for us. Would you agree with that statement? Maximum response is at the end of load duration, right? So here if you see this is Tm is at Td when your Td is equal to Tn by 2. Now when we start getting scenarios. Case 2, when Td by Tn is greater than half. Let's just see, which means that Td is greater or much greater than, there are two scenarios. Td is much greater than or much greater than, so the load duration lasts for a while, long loads. So in this case, if I put it into this equation, I am not going to solve it, but I will give you the expression. So this is, because you can play around with these numbers, 1 minus cosine. So in this case 2 pi, you can put Td by Tn, then 2 pi by Tn multiplied by T. We are not changing T. You are saying that this part of it greater than half. So try maybe half, 1, 1.5, so on and so forth, right? You can put that. So this is a number, this is a number, you have a function and you can plot that function to see. So try maybe on your own, or maybe this afternoon, plot this function for different values of, maybe that can be, I haven't tried this, but you can try this as a part of the tutorial. And so what you will see is, if you solve for this case, when T is greater than, you get X max when T is less than Td. So let's just say 1, right? Then 2 pi by Tn, you will see that when the maximum will occur when T by Td is less than 1. When or T by Td, or during the load duration. So what you get is, you get this the maximum response is before the load has passed, and I will draw some graphs. So, similarly, case 3 is Td by Tn is less than half. This is similar to the basically the positive phase duration is less than the time period. It is a very low time period. Though time duration or duration of time. Here the max response, again you can try putting that same expressions, and if some of you create that graph, you can show it to me or share it with me. So, the maximum displacement occurs after load has passed. Have you seen any of these phenomenon anywhere? Load has passed and then you get a maximum response? Probably not, right? None of the situations, static loads, maximum occurs when the load is maximum. So, we never have thought of response being dependent as a function of duration of the load, the dynamic footprint of the building, of that element. Is that a new concept, right? You don't have to agree with me just because I am saying right. So, I have not solved it for you, that is why, because there is no closed form solution, right, unless I give, that is why I put out here, try different values, and that is a clear function you can plot. You can plot, put some value for delta static, does not matter, and then you just plot a simple 1 minus cosine function and see how it goes.
Function 2 pi by Tn or Td in bracket.
2 pi by 2 pi or 2 Td, right? Yeah. Okay. Yeah, thank you for that. So, let us do, so the main idea here is that maximum displacement or the time depends on, the ratio of Td by, that is the main story to come out of this. You are not going to be again solving any of these to get your answers for most problems. So, let us see how to apply this to a simple structure. Finally, we get to an example. So, let us consider a wall, and these are just practical cases. This is a wall, height, typical height of a wall 12 feet, 4 meters or so, and let us say the wall is 30 feet, bays are typically about 25, 30, 40 feet, and this wall is supported, this is a curtain wall or a wall of an industrial building, let us say, and you have an I section right here. Looks like an I section, kind of, right? So, imagine this, if not, this is an I section. Is that called an I section here? We call it a W section mostly. Yeah, I sections, yeah. In the US we say either W section or an S section for some reason. W stands for white flange. So there's a reason why, but it's a nice section. And this is so the wall is subjected to a uniform pressure of 25 psi. So this is a W12 by 40. What it means is the nominal dimension is 12-inch deep and weighs 40 pounds per foot. The actual dimension could be plus or minus something. It's got a moment of inertia of 310. The XX is 310 in, and the modulus of elasticity is 29,000. This is for steel. Question is, for load durations TD equal to 5 milliseconds, 10 milliseconds, and I just chose a number with a reason, 7.3 milliseconds. So one is lower, higher, and you can go even if you want more than 10. Calculate the maximum value of dynamic deflection. And second is when so first step is to calculate the natural time period of the beam, of the structure, of the element. So what you have here is a uniformly distributed load and the magnitude of that is 25 psi multiplied by 30 times 12 inches. So what's that magnitude? 25 times 360, and this is 12. So I don't think if we need that, but yeah, we will need it. But does anybody have that number? $25 times 360. Let's even divide by 1,000. How much? 9. So 9 kips per inch divided by 12 is how many kips per foot? 3/4 or 9 kips per inch. So W is 9,000 pounds per inch, or so now the stiffness we have seen. I've shown this example, so I won't repeat it, and this is where for other applications we have seen. So in a situation like this, stiffness for this case, let me say discussed earlier, is You remember what the number was? What expression was? K is 384 L cube, right? So let's calculate that. 384 times multiplied by L is 5 L cubed, sorry. 5 times L is 12 feet. So this comes to, we are still in kips, still a very high, quite a high number, but it's in inches, 231.2 kips per inch. Then the mass, let's here is an interesting concept. So let's start with the beam. So the mass in this case is W by G. So this is 40 pounds, 12 feet divided by 384.6, or let's say 384 inches per second square, and units say pounds or kips, pounds and inches. So this gives us a mass of 1 point, because if I do kips, it's going to be a very small number, 1.25 pounds second square per inch. Would you do anything different or anything else? Do you have any comment? Do you want to stop me and say, ask a question, or say you're doing something not quite right, or do more, or you say, move on? You got to say something. You got to give me a break in speaking, right? Where do I stop? Mass of the beam I've taken, yes. W, oh no, this is, G is 384 inches per second square in that units. What could I be, you could be doing something if, and I wouldn't object. It's not hard. No, we are looking at mass. The topic is mass. What about the wall, right? Did that occur to you? Would you include the weight of the wall or not? And that's a good question. So I've not included it. We can try actually to see, let's just try that. Help me. Mass of the wall. Typically wall, I don't have it in my calcs. We'll talk of that idea. So the weight of the wall, let's say, is 25 pounds per square foot. Cladding weight, and then the tributary width is 30 feet. I have to give you the tributary width. Tributary width is 30 feet. So this is how much? 750. So the weight of the, by 12. So multiplied by, interesting, I don't know, maybe I'm at the end of the page. So help me with this. This is 25 times 30 times 12. How much? So 750 multiplied by 12, 7,500 plus another,
9,000.
yeah, 1500, so 9,000 pounds, divided by 384 is how much?
23.44.
Now, it's a pretty significant thing. In a design, you might, slab design or in a design, you would include it because that's a weight. So, the concept is it, the mass contributes to the inertia. Whether it contributes to your stiffness or not is the question. Here we are not, the inertia is coming only from the beam, right? So, you could include mass for dynamic, because if you are designing it a way to not disintegrate, it works with the system, right? The whole thing you have designed, let's say it's a concrete wall, perhaps tilt up wall or something, then the mass is contributing. How much it contributes to stiffness, that depends whether it's a composite construction. You're not going to do composite construction there. So, the stiffness contribution can be taken to be 0, but the mass contribution can be accounted for. We'll see, we'll do this calculation. I don't have it, but let's keep this in mind. So, let's look at the mass is 1.24. Actually, this thought just occurred to me, without wall, and equal to 24.68, because you see it's going to change. So, let's see without wall first. Without wall, the natural frequency is square root of k by m, square root of 231.2 kips per inch divided by, I need to multiply the units, multiplied by 1000 divided by 1.24, and if my math is right, and then my math is sometimes notoriously not right, you can check and feel free to correct. Not notorious, but sometimes. So, omega n is 431 radians per second, Tn is 2 pi by omega n, 2 pi by 431.8. So, this comes to 0.0146 seconds, or Tn is equal to 14.6. Let's add this with wall. Help me here, please. And let's see how the footprint, dynamic footprint changes. So, this time if the math is wrong, it's on you. 1000 pounds per inch divided by how much we said, 24.68. So, what is this number and what is Tn? You're all exploring concepts. Is anybody working on it? How much? 96.7. Which one? The first one? 96.8. And so the second one is Tn. 64. You see how let's look at responses too. Remember, idea is load duration divided by Tn. That's our mantra. So, having done this, the next step is static deflection. So, those are the dynamic footprints and dynamic deflection. So, here what you have is x static that does not change. Think it is 1296 kips divided by 231.2 kilopounds kips per inch. So, comes to 5.6 inches. Delta dynamic is equal to 2 times x static, which is, it's a fairly high number, 11.2 inches, but 25 psi is also a fairly high number. Is it practical? No. But, and its elastic behavior? No. But at this point we are studying the characteristics numerically. So, question is, when does the max occur? So, let us consider case 1. When case 1 is for just mass of wall not considered. We looked at 3 cases, three scenarios. Td is equal to 5 milliseconds. So, Td by Tn is 5 by 14.6 is 0.34. So, when does it occur? If Td by Tn is less than Tn by 2. No, Td by Tn is less than half, sorry, not Tn by 2, less than half. So, Td by Tn less than half maximum displacement occurs after the load has passed, right. We do not know when, but we will think I might, during the break I might have missed one thing, but we'll it will be a good time to pull that in also now. No, maybe not. Okay. Now, then B is when Td equal to 10 milliseconds, Td by Tn is 10 by 14.6. This is 0.68, which is greater than half. This is max occurs in this case before load has passed. And there was a reason, if you wondered why I chose a very odd number. Here Td by Tn is 7.3 by 14.6. So, in this scenario, this is at the end of load duration at t equal to. So, this is after when t greater than Td, t less than Td. So, the response is the same, this is elastic, but it is different. Now, let us look at case 2. Again, I have not done this. So, in case 2, what was Tn? 64 milliseconds. And Td, let us even consider the worst scenario, either 5 or 7.3 or 10 milliseconds. Let us consider 10. Td by Tn, what is 10 by 64? Point 16. So, where would it fall? In all cases, after, right? So, max response after load has passed. This is here. Now, we haven't gotten to a little more details. So, this one we will see, let me introduce you to this term. This, in fact, if it is less than 0.1, we call this close to an impulsive response. I will talk more about it or shortly. So, this is an impulsive response. This one, so again, so this is impulsive response. Here, what we call, this is before and this is, so there is a dynamic, we do not have a value high enough. So, we have something called a dynamic response and a quasi-static response. So, both of these would be considered more under what are known as dynamic responses. We have solved a very simple differential equation, but none of this is going to be a quasi-static response. We are coming to that shortly. So, the response of the structure depends on the ratio of Td by Tn, and it also depends on the Td by Tn, Td and Tn. So, what are these? I am coming to that in a moment. Next. So, any questions? Td by Tn actually, even if it goes up to 0.1 and below. So, in this case, if you see this, I would definitely say it is very close to an impulsive response. In all of these, this would still perhaps be dynamic too. Seismic is more dynamic, and there Td is very large. It might even go beyond duration depends on the natural. Look at the natural time period of this. This is only, even including the wall, it is only 64 milliseconds. Duration of your seismic is a minute, let's say, right? And wind is, of course, much, much larger. Now, consider with a rise time. So, this is TR. So, consider rise time. Now, if you have a rise time and this is, let us say, duration of the positive load. So, you have now 3 phases. I am not going to solve this. This is again mx double dot plus omega n square x is equal to, and you have seen that if this is P naught by m T by TR, then you are solving equal to P naught and equal to 0 for 0 less than T less than TR, TR less than T less than TD greater than. So, you have to set up, if you have a rise time that is involved back walls, you set that up separately. That is how they would solve. So, all these would be incorporated in your solutions. 12:45, right? Okay. We can get now to further solidify. Let us look at the SDOF response to a triangular pulse. So, we are looking at a scenario P naught TD. So, f of t or P naught P of t is P naught 1 minus T by TD for 0 less than T and equal to 0 for T greater than TD. So, here what they do, this is a complex phenomenon. You would consider an area, an impulse di at t, and the response is computed by, so if you are considering here, then you have to consider all these rectangles, and you can see that it is not only changing. If you consider somewhere here, you are going to consider the di here at t, another t, all these. So, you have to keep adding, and all these you can do. There is an integral, I think it is Duhamel's integral. You can use that technique to calculate the response analytically. So, the response now is broken into 2 parts. One during the pulse, as you have seen out there, and B after the pulse. So, for xi, I mean we have taken psi is equal to 0 undamped and 0 initial conditions. for during, you can write the expression as x of t is equal to p naught over k 1 by omega n t d sine of omega n t minus cosine of omega n t plus your particular part is going to look just like the, if you see here, the p naught 1 minus t over t d. So, that is the particular part of it. Now, this is during. Then after, if I can spell it, let us consider t prime is equal to t minus t d. So, expressing this, you have x of t prime is now the initial condition, somebody, we have talked about it, initial conditions is x, and so x at t prime equal to 0 is equal to x of t d from here, and x dot at t prime equal to 0 equal to x dot of t d again from, take the derivative from there. So, x of t d cosine, it is a free vibration problem, plus x dot of t d by omega n sine omega n t prime. This is for t greater than t d, and this is for t less than. So, the equations like this. So, let us say this is equation 1, this is equation 2. The concept equations 1 and 2, similarly for other loading scenarios, are used to develop what is known as a shock spectrum. So, once again I could have presented those spectrums, and but it's, at least I feel it's important to know some of its genesis. What is a spectrum? What do you understand by a spectrum? You've drawn spectral curves, response spectra. What else? Applications, huh? Yeah. So, for, as you said, various frequencies, you are finding some amplitudes. So, what does it really, what does the word spectrum mean? Same thing as you said, if you express it in words, your range, yeah, all possible range, you are looking for a response. Whatever be the response, in the range of values, what is, so that it is not a p versus t curve, that is the important. P versus t is a response for a particular frequency or whatever. Then you take peak values for each p versus t, and then you plot a response spectrum. So, a shock spectrum is also here. What do you think would be, if I were to ask you what my values or what my variables would be for a shock spectrum, x and y, what would you select? time versus x. But is that a spectrum? That is a response for a single. That's the first thing we talked about, right? Go ahead. TD by Tn, right? Where would that go? Yeah. So now you're representing. So in this example, for a particular TD by Tn, right? In this case, of course, all of it is constant. What would be the y-axis? In the, if it is, let me first draw the first answer. X versus t, you get something, whatever, x function, but this is a displacement history, pressure history, we'll call this displacement history, but now we want a spectrum. What would be the y-axis? X dynamic by x static. Usually spectrum are non-dimensional or if there is a dimension to it, you tend to non-dimensionalize it. Then the spectrum will look, that's how you, that's what we represent. It represents, a spectrum represents some, whatever be the variable, some peak value of a variable for a range of interest or range of, you can add something to it, right. See, that's what one of the things ways I feel I try to learn myself is take some equations or whatever and then write a sentence about it. Have you done this exercise and when did you do this last? Who asked you to, who would ask you to write something about something last in your education career? School, right? High school maybe. Your teachers, remember, they ask you to describe an apple or describe, and you have to write a sentence about it. There was a reason why. Because you present what you understand, not you visual. So the same thing, we stopped doing that in college a lot, but it's a good idea to write. You can develop your writing skills and then you can refine it. Then you'll see the more and more you refine, you get, see, getting very precise in writing is very important in communication. We have something called a 3-minute defense. Have you heard of it? So all even PhDs that you present has to be presented in 3 minutes. Imagine. What a concept. You work 5 years, what, I don't even get 50 minutes to present. Even 50 seems too little. How can I present? First response is when you defend is 50, I need 4 hours at least. The less and less you present, you're eliminating all the fluff and you're just bringing out the essence of what the story is. So try practicing that as you learn other things. But where we are going with this is where the positive phase, which is TD, is long compared to Tn, or TD much greater or much greater than Now we've got to go past the half Tn by 2, but the Tn by 2 was applicable only for constant load, right. We haven't, so still elastic behavior. And what is these, see for each, now Td, I have a Td, I have a stiffness, I have an omega n. If you want to try developing a maybe tutorial idea for developing a shock spectrum, more Excel work, and but if we do not have time, you can try that. What do you have to do here? You have a Td, you have a Tn, give that, plot this curve, find x max, you know x static, you get 1 point. Like that, plot for 20-30 points, you will get a spectrum, right. So, now it is nice to see it in a graphical sense. Do not ask me what x and y, it represents multiple things, load and response. If Td, again Td is long, it could mean what applications? Nuclear explosions, those kinds of other applications where you have a very long Td. So, the load curve, and it could be linear, the load takes a long time to dissipate. In this case, the response would be something like this, and this is what is known as quasi-static response. Remember the previous case with the wall is impulsive response. We will see later tomorrow other concepts. Again, mitigation wise, it can help to think of all these things. There is a lot of creativity actually. I mean, we don't, not too many people work or have opportunities to do blast design, but if you are creative, there is a lot of opportunities to be creative. Positive phase is short compared to Tn. So, Td is much less than Tn, let us say less than 0.1, previously we had 0.13416, so very small. Now, if I use the same plot here, this is time, the load drops, this is the load, but the response could be much after the load ends. This response is what we call as impulsive response. We will see more, we will keep seeing more of these concepts as we come along, and Td is similar to Tn. Here is where a lot of things break down and full solutions are needed. So, let us say this is your load, and the response could be something like this. So, it could be, here we see this is somewhere in between, but the response if you see is not, it is predictive, it has got a way here, if you see there is an oscillatory response in the dynamic period. It could be here, it could be just outside. Now where these numbers are, really there is no, this regime is much more difficult to predict. It's a dynamic response. So maybe in terms of Td by Tn, some guidelines 0.1 could be considered impulsive response from 0.1. This is accepted. So dynamic and Td by Tn quasi static. And in terms of Tmax, you have in impulsive Tmax greater than 3 Td. I mean, there is no number, I am just giving some ideas, somewhere between 0.3 less than Tmax by Td less than 3 Tmax by Td. The quasi-static peak response is somewhere here, start somewhere here. Tmax 3 times, this is 3 Td, and between those two. So you could also, for example, have something like this, whatever. Any of these are possible, as long as this is less than 3 Td. So we haven't introduced any files yet. So if you were to draw a shock spectrum, elastic, this is an elastic shock spectrum. And you know how to develop one by now. Maybe I do have. Maybe, oh, it may be in my, yeah. Wait, why did it open in a different? Did I say open as a new note? Or I hope I haven't lost what we had. Okay, so I think this has everything. Let's save it one more time. Oh, it did put in it. Oh, it's very big though. Okay, so now you see the maximum response ratio here. This is delta dynamic by delta static as suggested by you. I had nothing to do with it. Td by Tn. right. So, this is, and these are for triangular loads, half sine wave. This is not something we would do in rectangular loads. We have the equation, you should be able to get these two. If you see here, peak is at 0.5. And then it remains, whereas for triangular loading is the one that I drew. What is the maximum value it goes to? Roughly 1 point. So, it is less than even 2 for triangular loading. Similarly, if there are rise times or whatever other types of scenarios, you can develop that. So, let's maybe just stop and so summarize. If you see the tutorial, one thing is today you complete the problem from yesterday and compare the two methods. Secondly, plot the Friedlander equation for different z values, ratios z from 0.1 and compare. And the third is there is a small example. You can try, maybe, I don't know if you want to, if you feel this is I'm not, I mean, or you can try it later too for this case and see what you get. And then there is an example problem. I don't know if there, do you remember if the example problem is, do you know, Kavirasu, whether we have a shock spectrum in that solution or no? If not, we can push that part to tomorrow also, not a problem. Okay. All right. Well, thank you all.